for astrophysics, which is somewhat unusual for an applied physics student. And she actually worked in my group doing some of the early work on acoustic detection of ultra-energy neutrinos in seawater, kind of an exotic topic. And that was a project with one.
Okay, I know that was something you wanted me to check. Okay, so yes, today I'm going to talk to you about the present future of high energy neutrino astronomy. Yes, that is me at the geographic South Pole. This pole is, if you have a globe, right, the globe spins. So it spins around a stick. So that bottom stick, where that bottom stick intersects with Earth is here. And this is where the Earth spins around. So that's what that stick is, and I'm right next to it. Fun fact, if you're at the geographic South Pole, every direction you face is north, right? It's a lot of things break down. It's a lot of fun. I'm not going to talk about anything like that today, but I can't help but say these things when I show you this picture. Okay, so the prelude, which is kind of an intro to high energy neutrino astronomy, but also just a personal story of mine. So here's an image from the South Pole. This is at night or the winter. It's the same thing. There's one day, one sunrise, one sunset a year, right? So this is winter time, also nighttime. Here, our detector is buried under the ice, but all the cables come up to the surface. It goes across here, and then this is where we house our computers. So our computing facility, on-site computing facility, is in this building. Okay. I like this picture because you see two things I like. One is this light here. This is the southern lights, or aurora australis. So apparently if you winter over, which is the term you use to, so the South Pole gets too cold that basically you can't have flights in or out for about half the year. So what we do is we just leave people to take care of our detector, and we say, bye, see you in 6 months, don't kill each other. And then the sun sets, it's nighttime all year round, and you're with the same 30 people for 6 months. It's a very interesting psychological experiment, I'm sure. Anyway, what mainly people not volunteer, but apply to this job to do is to take these beautiful pictures and see the southern lights dance around. Apparently it's beautiful and life-changing. Still would not want to winter over, but lovely. Okay, so that's the one thing you see. The other big feature you see in the sky, this is our Milky Way. This is a cross-sectional view of our galaxy. So the Milky Way, let's see. So before I explain these slices, in case you're like me, that you went to a school where they had a good astro program but took 0 astro classes and don't know astronomy, our galaxy looks like this. It's a spiral galaxy. So it's a disk, basically, with spirals. It's bulged in the middle but flat, so it's like a pancake, right? And then we live inside the pancake on one of the spiral arms. So if you're inside the pancake looking towards the center of the pancake, what you see is the cross-section of the pancake. And that's what this is. So the Milky Way is a cross-sectional view of our own galaxy. So you straighten that up, put the galactic center in the center. That's this black hole right here. And you have your galactic plane map. So you go back, and this is the Milky Way, the galactic plane, seen in different wavelengths of light. So up top, still getting used to this pointer, sorry. So up top, you have radio, and then you go shorter in wavelength or higher in photon energy, however way you want to think about it, you end up at gamma rays. So this is the same view of the sky in different wavelengths. Okay. So this is a poster that NASA made a lot of, and this is from my student's office, but I bet you if you go to KaiPak, you'll see one or two of these in the hallway as well, or in the student's office as well. When I give talks at NASA, usually because of what is in here and what is not, they can tell what year the poster is from, which is a lot of fun. So yeah, every time I show this, there's always somebody at NASA that says, oh, that's that poster from, and I should remember the year by now, but I don't. So this is a very popular image, and what we've done now is we added another layer to this, and this is now in high energy neutrinos. So this is the same view, but now in neutrino emission. This is the first image of our galaxy in non-light, non-electromagnetic radiation. It's very blurry, it's very hard to know what it is, but I will explain it towards the end. And so this takes this image from a multi-wavelength view of our galaxy to a multi-messenger view of our galaxy, because you're now adding a different messenger in terms of particles, in terms of neutrinos. Okay, so when we saw this in 2013, we had this press conference at Drexel. We all suited up and pretended like we were serious people. Here's our article in Science. And we also did a lot of popular press as well, including this really nice write-up in the New York Times. So here, this is kind of a story of how particle physicists saw the first non-electromagnetic image of our own galaxy. That's the talk. It's also an intro, so I'm going to just review this. So here is a distance versus energy log plot. So as you go further away, you're looking at far things from you, right? So here's the center of the galaxy, that middle line of the strip I showed. But this is the next nearest galaxy, and then here are blazars and star formation max. So if you don't know that, that's okay. It just gets further and further. Here is it's a little bit trippy. Okay. Here is the here's the neutrino, this is the photon energy. So you have microwaves, optical, X-ray, gamma rays, so your photon energy is going up. And at some point in gamma rays, it gets hot enough, it gets high energy enough that the infrared and cosmic microwave background in the universe, you interact and pair produce. You produce electron-positron pairs. So your cross-section of this gamma ray becomes so high in space, which is not void, but filled with these leftover light from the early universe, that they don't make it to you anymore. So what's opaque here is things you can't see using photons, the energy and the distance. But we know that the universe continues to emit an extremely high energy because we've measured cosmic rays up to very high energies. So there's something out there emitting very high energy stuff, particles, light, and we want to know what it is. The photons probably don't make it out because they're too high energy and interact with the cosmic microwave background, the infrared background. You can measure the cosmic rays, but they are charged. They're charged nuclei. They're nuclei stripped of their electrons. So if that's the case, there's a lot of magnetic field between us and the source, whatever that may be, a different galaxy, a star. So the trajectory is not straight. So on Earth, the cosmic ray might look like it came from this direction, but maybe not. And what that means is that it's very hard to do astronomy with cosmic rays because you randomize the arrival direction. But you can still try. So this is all the high energy cosmic rays we've seen, very ultra high energy cosmic rays we've seen, put on a map of the sky just like these, and it's hard to see any structure, right? So what neutrinos provide in ultra high energy astronomy is this gap. It fills the gap between where the gamma rays end and the ultra high energy cosmic rays take over, but it also fills the gap between the resolved universe and the unresolved universe. And by resolved, I mean where do these things come from directionally is what I mean by resolved, right? In the astronomy sense. Okay, so that was the intro. Now I'm going to do past and present, and then I'll go to future. So the past and present of neutrino astronomy is really the birth of high energy neutrino astronomy in the past decade, which was a lot of first observations. When I gave this talk like 12 years ago, I would do air quotes neutrino astronomy because we talk about all these ways to see the universe, but we hadn't seen a single neutrino from outer space. Energy of particle in physics units up top. And then I like to give the equivalent amount of dynamite exploding in the bottom. So, you know, these ultra high energy cosmic rays, they're like 1 milligram of TNT exploding. That's how much that charged nuclei packs. This is very high energy. Okay, and this is the highest energy particles observed circa 2013. So by then, LHC was running very well, and we knew how to accelerate charged particles to maybe 10 TeV. The highest energy charged particle we've ever seen is cosmic rays. The highest energy neutral particle identifiable as a gamma ray was around here. And then in 2013, we saw a very high energy neutrino. It was around here. So this was the highest energy neutral particle ever observed. Here it is, that's the particle. So this immediately begs questions, right? So how was this particle made? So if we want to make a neutrino beam on Earth, what we do is we accelerate the charged particles. We know how to do that with magnets. And then we slam it onto a target, and the neutrinos come out. So is that what nature is doing? Is that what space is doing, right? Is some celestial thing out there, an astrophysical source, accelerating charged particles, as in making cosmic rays, ultra high energy cosmic rays, that's hitting some target and creating high energy neutrinos? Or is it created the same way the other neutral particles created, the gamma rays are created, right? Where was it created? How was it accelerated to such high energies? Just from the energy line, you can start asking questions. We saw more than just one neutrino that year in 2013. So this is a timeline we like to use to sort of advertise from IceCube, the sort of evolution of our experiment. So the detector was completed in 2011, and then it took till 2013 to see what we call diffuse extraterrestrial neutrinos or astrophysical neutrinos. And then we're going to go into these sources next. So I told you we saw more than one eventually. So this is our article from Science that year. Here is energy of the neutrino versus event count back then. This is 12 years ago now. Here are all the expected backgrounds from Earth and hashed lines containing all the expectations. And then the data seem to keep going. And the disagreement here is because we see neutrinos from outer space. We did a lot of press back then too, and we got a lot of popular press back then too. I wanted to include this here because this is a nod to all the science communicators. It is so hard to write an article that says, we found extragalactic diffuse neutrinos. Like, how do you say that in layman's term, right? So you can see them really trying. Alien neutrinos reveal new frontier in astronomy. Exotic space particles. I mean, that's one way to describe a neutrino. Right, but you can really tell them struggling to make this accessible to the common audience. And we obviously appreciate that. So 2013 is not long ago. Why did it take so long? So first thing is the size. So these very high energy neutrinos are rare. If you want to see rare things, you need a big detector. That's how that works. And so the biggest detector we had back then was Antares, which is a detector in the Mediterranean. This is a neutrino telescope in the Mediterranean. And then IceCube, which was already running by then, at the South Pole. So the first picture of me standing at the South Pole, I'm actually very high up. That's a high altitude picture. I'm on 2.8 kilometers of glacier ice. I actually got altitude sick there because I went from like a pressurized plane to 2.8 kilometers high. So what we do is we dig in the ice and we instrument the naturally occurring ice with 5,000 PMTs, and it's pitch black once you're 2.5 kilometers in the ice, and then you look for particles Cherenkov radiating. That's how all neutrino detectors work at these energies. So you can do that not just in the ice, but in the water. The Mediterranean is quite deep. You can go 2.5 kilometers down in the Mediterranean. Sunlight does not reach that deep. So you can put your PMTs there and look for particles, high energy particles going by and producing Cherenkov radiation. But these are really big detectors. Here, we had to figure out how to drill down 2.8 kilometers of ice. I mean, I say that in one sentence, but if you ask me to run 2.8 kilometers that way, it'll take a while. Now imagine digging ice 2.8 kilometers down. That's really hard, technically. Antares had to deploy these lines of PMTs in the water. Now water is not frozen, so it moves. There's currents, there's waves, and you're in a vessel, and you have a line that's 450 meters long, and you can't get them tangled when you deploy. So these are hard things to build. The large detectors are really challenging to build. But also, it's really hard to do neutrino astronomy because of the backgrounds. And this is really the problem in everything we do. So most of the time, these detectors trigger on atmospheric muons. So when a cosmic ray comes and hits our atmosphere, it creates a particle shower, and part of that is the long-lived atmospheric muons. And every neutrino detector has to go underground to avoid these. So we are as underground as we can be, but we still see a lot of muons. For every one neutrino from outside the Earth, we see 10 to the 9 atmospheric muons. So imagine your signal to noise ratio being 1 to 10 to the 9. That's what we have to deal with. On top of that, this shower creates actual neutrinos as well. And these neutrinos, even though they're neutrinos, they're not as interesting to us because they originate in the atmosphere. And that's about 1,000 to 1 in signal to noise. So it is what it is. This is our data rate, and we had to either wait for statistics or develop smarter ways to combat this, to see the signal buried underneath all this. We're a detector on 24/7. We've been running for 13 years. Our trigger rate is 3 kilohertz. That means we've been collecting 3,000 events per second for the last 13 years nonstop. So we are a large data, so big data science is what it is. And the name of the game is to smartly process these. Okay. So you're back in 2013. We've seen neutrinos from outer space. We don't know where it came from, but we see that there's more than what we should expect on Earth. But where do these come from? So here is a neutrino sky, and this includes more than just a handful of neutrinos by now. It actually includes a lot of background as well. The background is uniform, so what you're trying to do here is on top of the uniform background, try to see a hot spot of neutrinos. Neutrinos all arriving from the same location. So here is a sky map, and we look for the hottest spot in the northern hemisphere and the southern hemisphere. And what we do is we assign p-values. So this is, for example, that says p-value of 10%. That's the percent chance that a fluctuation in the background could have caused something so signal-like. So 10% of the times, a random background fluctuation can make something this hot, which is quite often that you would not consider that a source, right? So if you're looking at a very bright night sky, like let's say you're in city pollution, light pollution, and you're trying to see stars behind it, which is exactly analogous to what this is, right? And you can't tell if there's a star there or not because it's kind of light around you. You want to be sure that star is definitely not some background fluctuation. That's the percent chance that we use as p-values. This is 75%, so clearly background. And so we don't really see like a clear night sky vision like you expect, where you're like, oh, there's a source there, source there, source there. Those are the neutrino sources on the sky. In comparison, this is what a gamma ray sky map looks like. This is the Fermi 12-year sky map. And you clearly see, I mean, you don't have to get into statistical analysis like we do. There's something there, there's something there. You can just take up all the dots. This is the galactic plane. You know, you can even tell, even if you're not an astronomer, that you can do astronomy with that, right? So that compared to that. Okay. I don't know why this is still here. Sorry. Okay. But now in 2018, we have our first source. We identify the first thing that we can pinpoint and say, that thing produces neutrinos in the sky. And that is a blazar. Oh, sorry, did I not? Oh, everything is out of order here. That is a blazar. So here is Orion. This is Orion's bow, and that's his arm. That red circle is this red circle. And within it, so this is a very high energy neutrino we saw, and we were trying to localize it in the sky. And it came from Orion's arm. And within it was a flaring blazar called TXS 0506-056. What is a blazar? So here is the portion of the talk where a particle physicist explains what a blazar is. I'm always nervous when I do this. Please correct me for those of you in the audience who know better. So a blazar is an active galaxy with a supermassive black hole. There is a jet coming out of this black hole, and it's pointed at Earth. That's my definition that I got. So there is something there that's flaring, that was flaring in gamma rays, as Fermi told us. And at the same time, from the same place, we saw a very high energy neutrino. And that became our first detected neutrino source. So that's this. That happened in 2018. 2022, we saw a different kind of galaxy. Now we saw NGC 1068. So this particle physicist explains to you what a starburst galaxy is. Okay, this is a closer galaxy with high star formation rate. It has lots of gas and collisions. There's a lot of activity happening, and there's a lot of young stars being born in the environment. So that's a starburst galaxy. And we saw it, this came about just doing that map over and over. And eventually it got hot enough that our most recent map, we see this as a bright spot. So this is the first bright spot to sort of appear in the sky. And that's it. That is the two sources we have found that emit neutrinos so far. So these two are nothing alike. One is a blazar, one is a starburst galaxy. The other is a starburst galaxy. The one is far away, the other one is close by. There's nothing particularly special about these. And these aren't the first blazars or starburst galaxies we've searched. We've searched many directions, seeing if there's neutrinos coming from this known thing, that known thing, and always the answer was no. So we don't quite understand what makes these special. Why aren't they the same type of thing? Why don't things like it not emit neutrinos at the detectable threshold? If you asked anybody before 2018, what do you think would make high energy neutrinos? What sources do you think IceCube would see first? I think most people should have said gamma ray bursts. We don't see neutrinos from gamma ray bursts. Where are they? This talk is going to be a lot of open-ended questions, just letting you know. Okay. So then, sorry, I'm trying to see how this got disorganized here. I'm sorry about the slide order. Okay, so now I'm going to talk to you about the galactic plane. That's going to be the third thing we see in the sky, identifiable as high energy neutrino emitters. And before I do that, I have to talk to you about what we see in IceCube. So what we see in IceCube, and every single dot here is a PMT. And the bubble size is the amount of light we saw from the Cherenkov radiation. And the color is the timing. So it goes red, orange, yellow, green, and then I guess there's no blue. So here you can tell that there was a particle that zoomed, sorry, it's very hard to point this, zoomed this way because it leaves a trail of light first here, then here, then here, then here. So this is what we call the track event. It is caused by muons. Any muon will cause this if there is enough energy in that muon. What we think happened here is that a neutrino, muon neutrino, interacted with the ice over here, produced a muon, and then it traveled through. And you're like, well, how do you know it was caused by a neutrino, not a muon just coming through from the atmosphere? Well, muons can't travel this much. So this is slightly downgoing. So if you imagine yourself buried in 2.8 kilometers of ice, and you point slightly downgoing, there's a lot of density to get through until you get to the other side of the atmosphere. And muons can't live that long, not even at these energies. So we know that a high energy neutrino came, created a high energy muon, and it traversed through. And it provides these very nice long, we call it track events because it's like a track. So you can imagine that we can point back to where the neutrino came from, and at TeV energies, the neutrino and the muon are linear. So you know, I can tell you with this, okay, the neutrino came from here, plus minus maybe this error circle. There are other events called cascade events we see in IceCube, and what this is actually is a neutrino coming in, interacting here in the ice, and creating a particle shower. And this happens quite a bit, but what happens here is that the shower has direction and develops, but because our detector is so big, the shower itself is probably the size of this biggest dot you see. So you can't really see the shower or the particles within it, and the particles are short-lived. So the shower is short. But the light emitted from those particles is intense enough that it comes out. Now, if we didn't have any scattering in the ice of photons, it would come out beamed like the particle shower was. But because our ice is so scattery, and this is the optical property of our ice that we can't do anything about, it actually diffuses out as from a point. And we call that cascade because it's a cascade of light coming from one point. We know this is a neutrino interaction because a charged particle can't sneak in without emitting light at these energies and then create this much of a particle shower. So it has to be a neutrino. As you can imagine, the directionality is not quite clear, right? So these kind of cascade events, I can tell you, okay, I think the neutrino came from here, plus minus a big circle in the sky. And for astronomy purposes, we used to always throw these away because they don't point. But the thing is, as I said, IceCube, the name of the game is big data science with, horrible signal to noise, right? So reminding you that for every signal we want to see, there's 10 to the 9 background of muons and then 10 to the 3 of atmospheric neutrinos, which is not the right kind of neutrinos. So we need to fight against backgrounds. And it turns out all these backgrounds create tracks. So the trade-off I decided to do was, okay, let's forego this, even though it points in astronomy is better this way. I'm going to do this. That's going to help me with my signal to noise. I'm going to suppress my backgrounds. But instead, the trade-off for me is that I have blurry vision. I cannot resolve things tight in the sky. Everything becomes a blur. Okay, this is the idea I had maybe like 15 years ago by now. And then, and if you're, let's say you're nearsighted and everything is a blur in the sky, what is the first thing you might see? A tiny star or something big in the sky? Right, like the Galactic Plane, like the Milky Way. So that was my idea. So I embarked on this. My collaborators didn't believe we can do it, actually. And doubted it until the day before I unblinded, and then they got excited. Anyway, so my former postdoc, Mike Richmond, so what he did was every PMT, we have a waveform from the PMT. So I'm showing some of these waveforms from the PMT. That's the black crosses. Now, if the neutrino came, I know it's really hard to see, in the red direction versus 180 degrees flipped in the blue direction, right? Then the waveforms would have been red for the red direction and blue from the blue direction. And you see the blue fits better than the red here. And that's how you do directional. Yeah.
I can't read the horizontal axis.
Yeah, so yeah, it's time and it's time.
Light intensity versus time?
Yeah, photon, yes. It's the PMT readout. But so what you're doing is we have 5,000 PMTs and readouts, and for every direction, you can simulate what the waveforms in those 5,000 PMTs look like. But we want to do the reverse problem. We have the waveforms, 5,000 waveforms, and we want to know which direction the neutrino came from. So this is a very good problem for machine learning, and Mike was really an expert in deep neural networks, so he developed a DNN to do this reconstruction much better, that we can tighten that error circle, so our blurred vision got a little bit sharper. And then my PhD student, actually, former PhD student, now a postdoc at Maryland, University of Maryland, he did event selection. So I told you that the name of the game is digging for that signal neutrino, 1 in every 10 to the 9. So he used machine learning to do that better, and this is a plot of that, but I'm gonna go ahead and skip this. Just take my word that the event selection got better. And so what we did with the three of us is we were trying to see the galactic plane. So now I've actually switched the coordinate system, the projection on you. I'm very sorry. This is now an equatorial coordinates as opposed to galactic. So before I said the galactic plane was the center line here. Now it's not. And in this projection, it is this V-shaped line here. Very sorry. So the name of the game is, do these neutrino hotspots cluster around the line that is the galactic plane? So our 2-year data analysis is a no. 7-year data analysis, 2.1%. Okay, so that means that this amount of clustering of hotspots around the galactic plane, 2.1% of the times the backgrounds will randomly fluctuate to create something this interesting. Okay, that's not very anything to write home about, so no. And finally, when we looked at the 10-year data, we saw that only 0.004% of the time a random background fluctuation will cluster along the plane. And I'm actually putting a lot of details, sweeping it under the rug. It's not just the straight clustering along the plane. We actually have a detailed model of this and everything, but I'm not going to get into that now. And there's also energy reconstruction. I'm sweeping a lot of things under the rug here. But here is when we saw that galactic plane. So you straighten that line out, and it looks like this. Okay, so here is the optical view of the Milky Way in that strip format from the first part of the talk. Here it is in gamma rays. Here it is in the gamma ray portion, so this is not all of this, but just the portion where we think the gamma rays are created by pion decay, neutral pion decay. If there is neutral pions being created, there must be charged pions being created, and those decay to make neutrinos. So the charged pions decay to neutrinos, the neutral pions decay to 2 gammas. So if there is a gamma ray emission, diffuse gamma ray emission like that, then we must see the same thing in neutrinos. There's a lot of caveats, like these gamma rays measurements are 3 or 4 orders of magnitude lower in energy than what we're looking at and things like that. But I'm not going to get into details, but please ask me if you're interested. Now, so this is the predicted neutrino sky map. Now, we did the cascade events, right? You don't have to be an astronomer to do that, which is interesting. But another thing that you can ask is so this gamma ray map, actually, this is, you can see point sources, what we call point sources or stars, and truly diffuse things. And we can't tell yet from the neutrino map if this is caused by just stars along the galactic plane as opposed to a diffuse emission, a glow of the Milky Way. So we don't know that. We don't know what the ratio is of those two. I never mentioned energy, but we want to, so we just extrapolated the energy from photons 4 orders of magnitude up. And is that the right thing? We don't know. We don't have an answer for that. Again, there's blurred vision here. We cannot see individual features. So there's more questions than it answers anything, really. Is it there? Yes. Can I tell you anything else? No. And in fact, the situation is more dire than that. So I told you in 2013, we saw the first diffuse glow of the whole sky, not just along the galactic plane, but the whole sky in neutrinos. So that is extragalactic diffuse emission, right? So we know something out there in space, probably in all directions, is making high energy neutrinos. I told you we've seen 2 sources, maybe 3 if you count the galactic plane. They don't add up anywhere near the total diffuse neutrinos that we observe. So there has to be something other than those 3 things making it, right? So then this table is a little old and I should do this again, but it's also kind of a you can't do this in science kind of table. So what we do is we stack similar things. So we stacked, this is old, so it's TULAC, but these are the known blazars at the time from Fermi, a gamma ray telescope. And we stack them and we say, hey, there's 862 blazars that we knew about back then. Are there more high energy neutrinos coming from these 862 points in the sky compared to the rest of the sky? And the answer was no. And therefore, you can put an upper limit on the neutrino emission of these blazars altogether, right? And I can convert that upper limit flux into the percentage of the diffuse flux we actually measure. So this means that at most, 7% of the neutrinos we see can come from all the blazars in the TULAC catalog, Fermi TULAC catalog. 0% is also compatible, but it can't be more than 7. It can't be 8%, right? And you do this game with different species of galaxies and stars and other things, and you keep seeing no neutrino correlation, and you keep putting the upper limit in terms of the neutrino flux we've measured from the whole sky. And it's very low. This is at most what percentage of the measured thing can come from this specific type of astronomical sources. Not only that, and you should never ever do this, but even if you add up all these numbers, it doesn't get anywhere close to 100. So we really don't know what are making these high energy neutrinos that we keep seeing. Now I told you we see 2 sources, right? So one of them is a blazar and is actually a part of this. So one of the 862 is TXS 0506056, which we claim is a neutrino source. But the thing is, if you include it in 862 points in the sky all treated equally, it gets washed out, so you don't see it. So it's very possible that a subset of this, in whatever category you want of your sources, emits neutrinos. But then you have to say, well, what is special about this subset? How do I create a subset that emits neutrinos? And there's no subset that we've seen correlations with. So we really don't know we've measured the high energy neutrinos, the universe emits high energy neutrinos. We've localized 3 things, but beyond that, we don't know what causes it. And everything we looked at, it doesn't correlate. Is the situation. And that is the present. Okay, future. So I think the next decade, we really need to go towards answers. Because if anything, this last decade, we've proven that we can measure these neutrinos, astrophysical neutrinos as we call them, and we raised a lot of questions that we can't answer. Okay, so one thing, my soapbox thing is that if we really want to do multi-messenger astronomy, this is the idea that you'd use more than your E&M waves to do astronomy, we really need to become a more equal partner in this. So right now, what tethers neutrinos to astronomy really is gamma rays, because we're the closest we have in energy range. But we're still 3-4 orders of magnitude away. But anyway, we can't do any of this without having gamma ray. Source catalogs, sky maps, everything we do relies on gamma rays. Of course, the aim is to identify sources seen both in gamma rays and neutrinos. But you can also think of a situation, especially given the state of the field I just told you about a slide ago, where maybe we start seeing neutrino sources that are dark in gamma rays, or maybe even in more wavelengths than gamma rays, right? And what does that mean, right? So if we want to get to these kind of catalog building in neutrinos and also looking for dark sources and what have you, we just need to collect more sources. And we just need more neutrino telescopes, is to cut to the chase, is what I'm trying to argue here. And I don't think this is at all surprising. So, you know, if you want to have this very wide view, electromagnetic telescopes have different wavelengths and different field of views, and that's how they have such a successfully multi-wavelength program. So we need neutrino telescopes of wide energy ranges and wide field of views too. That's my argument. To give you a historical perspective, and I like this because it's kind of like we're not inventing anything new here in our path. Apparently, gamma ray astronomy started when launching high altitude rockets and seeing that the gamma ray radiation went up as you went to the sky. So this is the discovery of diffuse gamma ray radiation, right? So this is circa 2013 neutrino astronomy equivalent. And now you start, in the 80s, you start seeing the galactic plane, diffuse galactic plane in some discrete sources. And then this, right? X-ray astronomy. You see the diffuse emission of X-rays in the first source in the 1960s. And then in the 90s, you start seeing like a countable number of sources. And then you have X-ray astronomy, right? So if we're going to do the same game plan as multi-wavelength astronomy and multi-messenger, what we need is more and better telescopes. Okay, my opinion is we need three priorities to achieve this goal. I'm going to go, I think, 2, 3, and 1 in importance. So the first thing is complementary location. So I just told you that multi-wavelength astronomy is successful because we have telescopes all over the world covering different parts of the sky. Well, it's the same thing in neutrinos too. So here is a global map of what neutrino telescopes could be running in 10 years. This is all the existing and building and proposed neutrino telescopes. And sorry, what that gets us, first let me get to this. What that gets us is complementary peak sensitivity. So here is the sky. Here is IceCube, for example. This is our peak sensitivity. We're the most sensitive just around the equator, on top of the equator here, around the equator and on top of it in the northern hemisphere. The telescope in the Mediterranean has peak sensitivity here in the blue band. And then if we put one in the Pacific, it would look like the red band. So we are covering the sky with telescopes of different locations. Now let me tell you about these different telescopes just a little bit, because I know I'm running out of time and I don't like going long in my talks. So IceCube Gen 2 is something we're trying to make the IceCube detector bigger and better. KM3Net is the successor to Antares. This is the Mediterranean experiment. Now they're also trying to make it bigger and better. And P1 is the other telescope I'm involved in. This is off the coast of Vancouver Island in Canada. It's just bigger and better. I'll just leave it at that. Let me tell you about the New Hemisphere newcomers. So this worldview is very Eurocentric because it was made by a European collaborator, but of course the Pacific wraps around, as you know well, on this side of the continent. So these new telescopes are all in the western hemisphere. Anyway, the places where neutrino telescopes have not been before. There's 2 huge telescopes in the South China Sea that China is planning to build. And the scale is just ginormous. This is the one off the coast of Vancouver Island, P1, or Pacific Ocean Neutrino Explorer. I'm involved in this one. We want to actually do something very similar. We deployed 2 Pathfinder strings already, and we're on our way to deploying our first cluster, actually. We have funding for that. We have funding from Canada, Germany, and the US, so this is at least going forward to some degree, so I'm excited about that. And again, the worldwide view covers the sky. That's the point here. Okay, the third point is complementary technology. So this is a little hard to, I knew I'd probably have to skip this one. So I'm just going to say that for very particle physics-y reasons and optical property reasons, depending on what you want to target, which neutrino flux you want to target. So here is neutrino energy versus flux. And because it all just falls very steeply, you multiply by e squared to straighten things out. So this straight line labeled extragalactic is really e to the minus 2. It's falling. So depending on what neutrinos you want to target, so here's the atmospheric neutrinos. I told you this was our background, 1,000 times our space neutrinos, our astrophysical neutrinos. This is the galactic neutrinos. This is the one I just discovered 2 years ago. Here's the extragalactic neutrinos. This is the one we measured since 2013, and we can't resolve where they're coming from or what causes it. Another component of neutrino flux that I didn't talk about is called the GZK or EHE neutrinos. This comes from ultra-high energy cosmic ray predictions. Anyway, so these are the 4 different neutrino fluxes, and depending on what you want to target, you want to use different technology. And for galactic versus extragalactic, which is what I'm most familiar with, there are, for reasons, which I'm happy to get into after the talk, ice is better for extragalactic. Water is better for galactic neutrinos. So even the different types of neutrinos give us different energy range sensitivity and target different components, is my argument here. I think this is a good sign. So now, you went from 1 neutrino telescope to like 5. What are you doing? Well, actually, I think what we're doing is we're diverging optimizations, which is a good sign of a maturing field. Before, we didn't know what we were doing. We had never measured neutrinos from space before. So we were all racing to be the one telescope to do it all. And now that we've started measuring components of astrophysical neutrinos, we have different technologies and locations and ways to optimize for different things. And that's how you want to see a field evolve, I think. But really, at the end of the day, what matters is instrumented volume. The fundamental challenge for all neutrino telescopes is the high background rate, right? We need statistics. We're always statistics hungry, even though we're a big data experiment. More neutrinos above background. More PMTs we can deploy anywhere in the world, more photocathode coverage around the world, more data, more signals collected. It is as simple as that. So here is, everybody who says they'll be running a neutrino telescope in 10 years. Here is the instrumented volume. This is not effective volume. This is just instrumented volume. And if we can do this exponential increase, which I am not that naive, but if we can do a little bit of this, it'd be a good place for the field to be in. Okay, so let me conclude. IceCube started a new era of neutrino astronomy. We see the galaxy for the first time in neutrinos. Very proud of that. But really, all of this in the last 10 years, I think we just raised more questions, which is good because we want to answer it in the next 10 years. I think in order to do that, we need to become a stronger partner in multi-messenger astronomy. And in order to do that, I think we just need more telescopes to identify more sources, different telescopes around the world in different locations using different media to detect different components of the neutrino flux. And that's where I want to take the field in the next 10 years. Thank you.
What's the most likely overlap between gravitational wave events? What astrophysical object?
Yeah. So, yeah. So, I mean, the dream is to have all 3 detect the same thing, right? I don't know. I think it depends on who you ask. I'm pretty sure people are satisfied that binary neutron star mergers won't create neutrinos for modeling whatever. And then you're looking at a little bit more exotic things that we can all measure together. There's also, at some point, everything creates neutrinos, right? So it's just a threshold problem for us. You can just put it on us and say that. I think that's true. And we do look, every time there's a LVK alert, a gravitational wave, alert, we do follow up in that part of the sky, even without knowing what it is. So yeah, I don't have a good answer for you is probably my answer. And if you ask the model builders, the theorists, they will probably give you various answers and possibly not common with each other.
Yeah, in your neutrino map
Yeah.
of the galactic center,
Yeah.
how many events are we talking before you blurt it out?
Yeah. So we expected maybe of order 6,000 to 7,000, and that's what we see here. This one, yeah. So this is actually not a counts map. I'm sweeping a lot of things under the rug because it's not just straight up counts. The backgrounds are supposed to be lower in energy because of the flux, the softness of the atmospheric spectrum. The galactic flux is supposed to be a little bit harder than the background flux, which means that the more energetic you are as a neutrino, the more likely you are to not be background. So we factor all that in a likelihood analysis, and this is like actually a likelihood map. So it's not straight up counts map, the heat map. So it's a very processed map.
So 7,000 events got put in a computer program, and you ground away and did some stuff, and this is what came out.
We put in 1 million events, put it in a computer program, and the 7,000 is what came out in this way.
That includes, this is the burst signal.
No, this is steady emission. This is from, I want to say 10 years of data.
You know what I mean is when you're filtering events,
Yes.
and you're filtering the isolated burst events, not the tracks.
Oh, yes, I'm sorry, yes. These are all the burst events, yes.
Very complicated analysis.
Yes.
I didn't follow exactly.
I didn't explain it either.
Correct,
yes.
And then some of those are muons, atmospheric.
Yes.
Okay, and so you have a statistical likelihood filter thing to get rid of those.
There are filters to deal with things that don't reconstruct well, that won't help our analysis. There are filters to get rid of lower energy things, again, won't help our analysis. We're trying to get to a point where we have a manageable size of a data set, which reduces the 1 million to probably about, I want to say like 10,000, 100,000, and then we do a likelihood analysis on a template of what we think the neutrinos should look like, where they should cluster, and what energy they should have. And we try to separate the background, which is uniform, versus that template of signals.
Just a hypothetical mark. I'm a lowly theorist, okay? And when I look at something like this, what I want is the data, and not F of data. And I'm hearing you that this represents the galactic plane somehow. But too many words and not enough equations. So I can't.
Okay.
I find it can't follow.
This is like the opposite of what I was told to put on a slide. Did I even keep it? I think you guys are laughing about this. This is my hedge for when astronomers ask me tough questions. I was like, you guys don't even know what Asian unification is. And I got this from an astronomer. Anyway, sorry, besides the point here. This is what we do. So here's our...
Are you plotting L of x?
Yes, I am.
So L of x is, x is a two-dimensional thing, position in the sky?
Correct. Positions in the sky in this case, yes.
And so S and B are these theoretical.
S is the signal PDF that we assume, and in this case it is the galactic plane template in both energy and spatial
So you put
template.
what you expect the experiment to look like into the analysis of the data.
Yes, and also the background. And what it tries to do is it tries to balance with all the data, how much should belong in the background bucket and how much should belong in the signal bucket, and tries to balance them. Yeah.
So how big a detector do you need before you don't have to do this? We just take a picture of the galactic.
I'm going to say never, because it's an irreducible background. It's like trying to do astronomy in downtown Los Angeles, right? Like just,
Mount Wilson.
well, okay, within the, yeah, not up above. Yes. I'm not sure just time can ever really catch up, because the backgrounds are so bad. Yes.
Yeah, I want to make some comments about your calculation of contribution of some different
Yes.
sources to the
It's a bad table. I hope nobody ever sees it outside this room.
I wouldn't despair about that. That is it for one reason. Intergalactic gamma ray have been observed for much longer time. We still haven't found a complete description of what the extragalactic gamma ray type
Yeah.
of radiation comes from. We have a lot of information about sources, and everything we do comes to 70–80%, but not 100%. And this is because there are a lot of unknowns.
Right, right.
You need to
Unresolvable.
function, you need how they evolve
Yeah.
in velocity, how they evolve in density. And we have some idea about gamma ray, but we don't have any idea about those are neutrinos.
No.
So I don't know your estimates. Where did they come from? I have no idea.
Right. So it's very crude, right? We say, okay, we saw one blazar emitting neutrinos, so let's put all blazars in a bucket and see if there's neutrinos coming from all of them. Or we sometimes do a little bit more clever things and say, okay, let's make them scale as the gamma ray intensity. Let's say that the neutrino intensity follows the gamma ray intensity, and then put them in a bucket in a weighted way and see if the neutrinos come from there. So within this, I'm hiding a lot of things that matter a lot. In fact, one thing I'm hiding is the energy spectrum. So if you tweak that a little bit in the assumption of what it should be, these numbers will fluctuate wildly. So I hope the spirit of the table is more what gets communicated than the actual numbers. One reason compared to gamma ray astronomy that worries me a little bit is that this is the horizon problem. So at some point, you're too far to see gamma rays, right? Neutrinos, you don't have this problem. So suppose you could be in a situation where every high energy neutrino ever created at any distance can still come to you, mostly unaffected. So if you see everything, how do you see anything is kind of the existential dread.
But the low-energy gamma rays universe is pretty transparent.
That's true. And you can see, yes, that's right. So, cross fingers for inhomogeneity, cross fingers for handful of strong local sources. Yeah. Hope that the next generation of detector is enough to see what we would consider a first catalog of neutrino sources. I think that's the goal for now. Yeah.
One more question? Okay. Good, actually, so I'll ask you. So what's the schedule for the upgrade of IceCube?
Yeah, okay. I don't want to talk about this.
Apart from other...
Yeah, no, yeah.
Just from the technical standpoint, the schedule like as it was 6 months ago, let's say.
Sorry, there are tear-offs on importing the data from the South Pole.
Look, I don't even have the. So there's the answer I'll say on mic, and then the answer I'll say after we stop the recording, right? So the answer I'll say on mic is we are ready to go in like 5 years. If you give us a 5-year, takeoff period, we will know how to build this. We have a TDR technical design report out, a white paper out. You can find those in the archive. They've been out for a while now. And to get technical, we were invited to put in an MSRI for exploring how to build this year. So we're on track is what I'll say on record. And then once we stop, there's a whole other issue about access to Antarctica, access to South Pole Station, priorities about Antarctic science that are less rosy. Let me just keep it at there.
Okay, on this note, thanks Naoko again.
Thank you.